Hello and welcome everyone. In the last set of podcasts, we talked about energy and the laws of thermodynamics. And we ended with a brief discussion on delta G. What we want to do in this podcast and the next couple podcasts, we want to talk about how we're going to use that energy in cellular reactions. So we're going to talk about three big topics here, main topics, I should say. The first is we're going to talk about enzymes and catalysis. In the next one, we're going to talk about free energy, a little bit more on free energy than what we talked about on the last set of podcasts. We're going to talk about how that free energy is used in reactions, in catalytic reactions. And then we're going to end with a very brief discussion on activated carriers. That'll be important as we move forward in the semester. Okay, so let's go ahead and get moving with our discussion of enzymes and catalysis. If you remember, in the last podcast, we talked about delta G. And we said if it's a negative value, that it's a spontaneous reaction. This shouldn't be confused with the idea that it's just going to happen with no energy input at all. Spontaneous reactions still have some energy to overcome in order to achieve the reaction. Your book describes a scenario of burning a piece of paper, and I think this is a pretty good scenario. Paper plus oxygen can proceed to burning up, and it would generate smoke, some heat, certainly, some ash from the paper, carbon dioxide, and some water. Again, this doesn't occur automatically. Otherwise, the book on your desk, the book on my desk, would be at risk of just igniting. It would lead to a very interesting set of circumstances, but this doesn't happen automatically. It requires something for this to happen. For instance, maybe a match, to provide that energy necessary for the paper combined with the oxygen to burn to produce these products. It's still a spontaneous reaction. It still would have a delta G of a negative number, but it's not going to occur automatically. We can think of it in this graph, and that is this scenario here, where over here you have your reactants, and over here you have your products. The reactants have a lot more energy, so they will have a tendency to go downhill to a lesser form of energy. But in order to do that, they have to get over this hump here. And this hump is something we call the activation of energy. So from here to here is the activation energy. We can think of the activation energy as an energy barrier that the reactants must get over in order to produce the products. In some cases, this activation barrier would be very difficult to achieve. What enzymes do is they lower the activation energy. So maybe it's like that with an energy, with an enzyme. In which case the energy of activation is now this value here. So you can see the blue here without an enzyme and the purple here with an enzyme, how the activation of energy has been lowered, which now makes this reaction much more probable. A term that we didn't use that I'd like to define real quick, the ability for the enzyme to do this, we say the enzyme acts as a catalyst in the reaction. The catalyst accelerates the speed of the reaction. In our example up here, the catalyst was the match. It provided the heat and the energy to ignite the paper with available oxygen to produce these products. In biological reactions, usually it will be an enzyme that acts as a catalyst. So how do enzymes work? Well, let's talk about that next. So how do enzymes work? Well, let's say you have a reactant. We'll draw it looking something like this. That is our reactant. And it's going to go through a reaction, a spontaneous reaction, to produce this as our product. How does the enzyme help do that? The enzyme that's going to come in here. Well, what the enzyme will do is it will draw something kind of generic here. It will hold the substrate in such a way that it applies pressure to the bonds on this substrate here. By applying pressure on those bonds, it can stimulate the change to this, the breaking of those bonds. Maybe this could happen without the enzyme, but it would take a very long time for those bonds to have the same amount of pressure applied to them to create these two products. Let's look at another reaction. In this reaction, let's say we have these two reactants. And through this chemical reaction, what's going to happen is they're going to form this structure where they're now connected. Maybe without an enzyme, these two reactants might combine in such a way, might find each other, and the bonds might form in just the right places to produce this. But often enzymes can help stimulate that preferred interaction. In which case you might have an enzyme that looks something like this, where it will hold each of the substrates in such a way that the preferred binding sites of these two substrates are right next to each other, which simulates or stimulates the bonding of those two to produce this proper product. I'm not sure if I mentioned this specific name, but it's an important thing to remember. And as these two sites here, and the one site on the last one I drew, we call these active sites. I should also mention that when these substrates bind here, sometimes the enzyme will change its shape. However, once it's released the substrate, it will resume its normal shape, its pre-bound shape. So now I want to spend a little bit more time talking about these active sites and the rate at which they are bound. So let's pretend we have this system. Why don't we call it a cell? Cell biology class seems to make sense. And in this system, we have several enzymes. And I'm just going to draw the enzymes like so, nothing too fancy. And each of these enzymes has an active site. And I'm just going to show that by a dot. All these enzymes should be the same size. I just wasn't very careful, I apologize. But we have a fixed amount of enzymes with a fixed amount of active sites. As substrate is introduced into the cell, it's going to quickly bind to these enzymes, because at that point the substrate is low. And let's draw the substrate as these purple dots. And it's going to come in here and it's going to bind here, it's going to bind here to these various active sites. The more substrate that is added, the quicker these sites get bound with substrate. Now it's going to be turned over to the product and then they'll be able to be used again. That's what enzymes do. They constantly are reactivated. But there will be at some concentration of substrate where it swamps out these active sites, that you can't really add any more substrate to it to make the rate of the reaction go any faster. So let's draw a graph here. And then we'll draw this line. Like so. On the vertical axis, we have the rate of the reaction. On the horizontal axis, we have the substrate concentration. So as you're adding substrate, the rate will go up pretty fast. But at some point, these active sites become completely filled, and it doesn't matter how much more substrate you add. We call this rate at which all the active sites are full, we call that Vmax, the maximum velocity. The amount of products you're going to make at that point is strictly dependent upon how fast that enzyme can release the product. I want to talk about one other term here, and it's a term that we're going to call Km. And it is, let me go ahead and draw it first here. It stands for the Michaelis constant, after one of the scientists that came up with this calculation. We can think of the Km as the concentration of substrate that the enzyme works at half the velocity. So I didn't write it, but what we have here is half Vmax. So this Km value has some implications to enzymes in the cell. You can think of a small Km as being characteristic of an enzyme that binds tightly to substrate, where a high Km relative to other enzymes we're comparing would indicate an enzyme that binds weakly to substrate. Alright, we'll talk about enzymes later at various points throughout the semester, but I think that's all I want to say about them right now for this first podcast. In the next podcast, we're going to look at delta G, we're going to look at equilibrium constants, and talk about how we apply those.